Welcome to the deep dive. Today we're asking, a really big question. Why do quarks and leptons, the universe's fundamental bits, have the masses they do?
Exactly. We've got some theoretical work here suggesting they might not be the bottom layer.
Right. It proposes they're made of even smaller things. Rishons, is that the term?
That's it. Generic and flavored rishons interacting with something called scalar bosons.
Okay, so the mission for this deep dive is to sort of unpack this model, see how it tries to explain these masses we observe.
Yeah, the core idea is deriving these masses from the properties and combinations of these, well, more basic parts.
Like ingredients in a recipe determining the final weight.
Pretty much. And it uses a specific measuring stick, electron units, for mass.
Electron units, okay. So everything's measured relative to the electron's mass.
Right. It gives a consistent base for the rishons themselves and, crucially, for all the particle masses that come out of the model.
All right, let's dive in then. Starting with quarks. The sources talk about generic quarks.
A generic D quark at 200 electron units and a generic U quark, much heavier, at 2,000.
2,000, okay. So how do we get the 6 quarks we actually know from just these two?
That's where these scalar bosons come in. There's a 0, a plus, and a minus type.
And they have combinatorial values. What does that mean exactly?
It's basically a number associated with them that influences how they affect mass. They introduce mass factors, multipliers, or divisors.
Right.
For quarks, it's often 2, 20, or 200.
Got it. And the boson plus does something extra, like an electromagnetic influence.
Yeah, it can actually flip a quark type, like a D to a U.
Okay, let's test this out. The top quark, the heavyweight champion. How does the model build that?
Okay, so the top quark is proposed as a generic D quark plus a scalar boson plus.
Generic D quark, that's 200 units to start.
Right. Now, the whole system, the top quark combination, has a total combinatorial value of 3, because it's not 1.
Ah, that triggers a mass factor.
Exactly. The boson plus brings in a big mass factor.
200.
Okay, a factor of 200. Right. And the quark flip. Yes, that electromagnetic influence from the boson plus changes the initial D quark into a U quark.
Which has that generic mass of 2,000 units.
Right. So you take the 2,000 units from the converted U quark and multiply by the boson plus's factor of 200.
2,000 times 200. That's 400,000 electron units.
Whoa, a huge mass, yeah. And the model explains it through that combination and the strong multiplier.
That makes sense. And the source notes, positive times positive combinatorial values mean mass increase. Okay. What about the bottom quark? Still heavy, but not that heavy.
A bottom quark also starts with the generic D quark, 200 units, but this time it combines with 2 boson zeros.
2 of them, okay.
The total combinatorial value is again 3, so we expect mass changes. The first boson zero adds a mass factor of 2.
So 200 times 2, 400 units, intermediate step.
Exactly. Then the second boson zero comes in, and its specific combinatorial value acts like a multiplier of 20 on that intermediate mass.
Ah, okay, so 20 times the 400 units.
It gives you 8,000 electron units for the bottom quark.
8,000. Still hefty, but way less than the top. It really shows how the specific bosons matter. Okay, moving down the scale. Charm quark.
Charm involves a generic D quark and a boson plus again. But here's the twist. This boson plus has a combinatorial value of 0.
0. So does it still do the quark flip?
Yes, it still converts a D quark to a U quark, giving it that 2,000 electron unit mass.
But no mass factor.
Exactly. With a 0 combinatorial value, it doesn't contribute a multiplier or divisor. So the charm quark's mass is just that converted U quark mass.
2,000 electron units. Simple as that in this case.
Okay. And the strange quark, lighter still.
Strange is a generic D quark plus something called a flavored boson zero.
Flavored boson zero. And the key here is the total combinatorial value for this setup is 1.
Ah, and you said earlier if it's 1.
Then the scalar boson doesn't change the generic quark's mass. No mass factor applied.
So the strange quark just keeps the mass of the generic D quark it started with.
Precisely. 200 electron units.
Okay, that covers the 4 heavier ones. Now the ones we see all the time. The down and up quarks. How does the D quark itself get formed in this model?
Well, the D quark is proposed to be a generic U quark.
Starting heavy at 2,000 units. Interesting.
Yeah, combined with a boson minus. This boson minus has a combinatorial value of -1.
-1. Okay, so mass decrease.
Exactly. A negative value here means division. It divides the mass by a factor of 200.
So 2,000 divided by 200, that's 10 electron units for the D quark.
A big reduction. And the source mentions that a positive times a negative combinatorial value generally leads to mass decrease, like division.
Right, that fits. Now the U quark itself, seems there are a couple of ways the model builds it.
Yes, 2 configurations proposed. First one, start with a generic D quark, 200 units, at a boson 0 and a boson plus.
Okay, d quark, boson 0, boson plus.
The boson 0, in this context, divides the mass by a factor of 20.
So 200 divided by 20 brings it down to 10 units.
Then the boson plus comes in. It does the conversion from D to U, and in this specific setup, it seems to assign an intrinsic mass of 5 electron units.
5 units. So division, then conversion, giving 5. What's the second way?
Second way also starts with the generic D quark, 200 units, but the order involves a boson plus first, then a boson 0.
Plus, then 0. Okay.
Yeah, the total combinatorial value isn't 1 here. The boson plus causes a division by 2.
200 divided by 2 is 100 units.
Then the boson 0 acts. It's described slightly differently here, maybe flavor generic Rishon switched, but it divides by 20.
So 100 divided by 20, also 5 electron units.
That's right. 2 different paths, same result for the U quark mass.
Interesting consistency. And the sources seem to suggest this picture for the light quarks matches reasonably well with the standard model values.
Yeah, especially for these lower generation quarks, the schema seems to align quite well with observed masses.
Okay, that's a lot on quarks. Let's switch over to the leptons now. Electrons, muons, neutrinos, how does the model handle them?
So, similar idea. We start with generic leptons. There's a generic electron, which the sources equate to the muon.
The muon. So the generic electron is the muon in this picture. How massive?
200 electron units. And there's a generic neutrino, which is the muon neutrino, much lighter at 125 hundred thousandths of an electron unit.
Wow, tiny. 0.000125 electron units. Okay, so those are the starting points. How do we get the muon itself then?
Well, since the generic electron is the muon, its composition is simple. The generic electron, 200 units, plus a boson 0 that has a 0 combinatorial value.
0 value again. So, like with the charm quark, it doesn't affect the mass.
Exactly. The only combinatorial value that matters here is from the generic electron itself, which is given as -3. The boson 0 adds nothing to the mass calculation.
So the muon stays at 200 electron units, consistent with its definition here. Okay, what about the muon neutrino?
The muon neutrino is proposed as the generic electron, 200 units, interacting with a boson plus.
Boson plus again. Does it convert it, like with quarks?
Here it says it inverts the particle. Basically turns the generic electron into its neutrino counterpart within the same generation, the muon neutrino.
And the mass. Does the boson plus add a factor?
No. Similar to the muon case, the combinatorial value comes only from the generic electron, nadather 3. The boson plus doesn't add a mass factor here.
So the mass just becomes that of the generic neutrino.
Right. 125 hundred thousandths of an electron unit, 0.0000125.
A huge drop just from that inversion by the boson plus. Okay, now the electron itself, our familiar electron.
The electron is the generic electron, 200 units, plus a scalar boson with a combinatorial value of 2.
Okay, so generic electron is nettedly combinatorial value. The boson is +2, negative times positive.
Means mass decrease, division.
Ah, division. By what factor?
By a factor of 200, according to the source.
So you take the 200 units of the generic electron, divide by 200.
And you get 1 electron unit, the definition of our baseline mass.
That works out nicely. It explains the muon electron mass difference just by changing the boson involved. Okay, now the electron neutrino, even lighter. How does that work? Looks like there are 2 ways again.
Yeah, 2 formations describe. One pathway involves the electron kind of converting to a muon, then to a muon neutrino. It results in a division operation yielding a mass of 625 hundred millionths of an electron unit.
So 0.000000625 electron units. Incredibly small. What's the other path?
The other path starts with the muon neutrino, which is 125 hundred thousandths, right?
0.000125.
And it interacts with the boson 0 that has a combinatorial value of 2.
Okay, so the muon neutrino is -3 combinatorial, boson 0 is +2, negative times positive, another division.
Right. It leads to the same resulting mass for the electron neutrino, 625 hundred millions.
Same result again. It's interesting how these different combinations seem to zero in on the same value, and the source mentions something about Rishons canceling out.
Yes. In one of the electron neutrino compositions, it's noted that the generic Rishons effectively cancel, which might suggest why it has such an incredibly low mass, almost 0, a kind of fundamental unity.
Fascinating. Okay, 3rd generation leptons, the tau, heavy one.
The tau lepton is built from the generic neutrino, 125 hundred thousandths, plus a boson minus.
Generic neutrino, -3 combinatorial, and boson minus, -1 combinatorial, negative times negative.
Gives a positive result, mass increase, multiplication.
Okay. Does the boson minus also convert anything?
Yes, it seems to first convert the generic neutrino, muon neutrino proxy, into something more like a muon, a charged lepton state, and then the mass factor is applied.
Multiplying up from that tiny neutrino mass.
Right. The final result is 4,000 electron units for the tau lepton.
4,000, a huge jump. Okay, last one. The tau neutrino.
Tau neutrino is the generic neutrino, 125 hundred thousandths, plus a boson zero. But this boson zero must have a negative combinatorial value here.
So negative times negative again. Mass increase.
Seems so. Negative from the neutrino, negative from this specific boson zero interaction, leading to a mass increase. The result is 25 thousandths of an electron unit.
0.025 electron units. Okay, so we've walked through how this Rishon and boson model attempts to build up all the quarks and leptons from just a few pieces and rules.
Exactly. Using these generic masses and the combinatorial values dictating multiplication or division.
Now, you mentioned something earlier, or the sources did, about a pattern comparing masses within a lepton generation.
Yes, this is really interesting. If you compare the charged lepton mass to its neutrino mass in each generation, for the tau and tau neutrino, it's 4,000 divided by 0.025.
Which is 160,000.
Right. Now, the sources note a potential discrepancy with the muon numbers provided, suggesting 1,600,000, which needs flagging. But the electron-electron neutrino masses are also related by a reciprocal factor. The main point highlighted is this generational factor, potentially the 160,000.
160,000 electron units. And why is that number significant?
Because the sources state this factor is comparable to the mass of the W boson, and they identify it as potentially the mass of the weak interaction particle of the generation.
So linking the mass differences between leptons directly to the mass of the particle that mediates the weak force, which allows leptons to change type, that's quite a connection if it holds.
It's a potentially profound link, yes. Suggesting the mass hierarchy isn't arbitrary, but tied deeply to the fundamental forces.
And overall, the model seems to get quite a few things right, or at least in the ballpark, especially for quarks and charged leptons.
That's what the sources suggest. Good alignment with standard model values for many particles. Neutrino masses are obviously trickier, still debated, even in the standard model.
So wrapping up this deep dive then, we've looked at this theoretical schema where quarks and leptons aren't the end of the line. They're composites of Rishons and scalar bosons.
And their masses emerge from the properties of these constituents, particularly these combinatorial values and mass factors.
We saw how different combinations could explain the huge range of masses, from the tiny electron neutrino up to the massive top quark.
And that intriguing potential connection, the 160,000 electron unit factor in lepton generations, possibly linking to the W boson mass.
It's a complex picture, and obviously theoretical, but it's fascinating how it tries to build everything from simpler parts.
Definitely. It makes you wonder about that underlying structure, if mass isn't fundamental, but emergent from composition and interaction.
Yeah, it really gets you thinking. Could an approach like this, a compositional one, genuinely lead to a deeper understanding? Maybe explain things the standard model currently just measures? And what else could you predict from a model like this? Something for you to ponder after this deep dive. Thanks for joining us.